In this video, we'll talk about a full algebraic solution to the consumer's problem. The method we use is called the Lagrangian. So far in this section, we built a model of a particular type of consumer's choice problem. In this problem, the consumer chooses a number of goods to purchase that best suits their preferences while using limited resources. In the previous video, we went through a lot of hard work and reasoning to identify and interpret the graphical solution of this problem. And we highlighted the tangent condition is the key leading to the optimal solution. However, repeating the graphical approach seems quite taxing as a general approach. So, is there an alternative way to solve this problem other than reasoning through a graph each and every time? The answer is yes. And this is what we will try to address now. In this video, we will explain a formal algebraic approach that leads us to the solution of the consumer's problem. If we take a step back to think about it, we will realize that the essence of our problem is to find quantities that maximize the value of the utility function, while making sure that the quantities stay under the budget constraint. In slightly more abstract terms, we're simply trying to maximizing a function by choosing some variables, while these variables are subject to a constraint. It turns out that there is a specific mathematical tool to systematically address this type of problem, which is called constraint optimization problem in general. There are wide applications of this tool in physics and engineering, as you can imagine, and it is also a workhorse in economics models. It is very useful to learn this approach, which holds the key to analyze many more sophisticated economics models. So now let's try to formulate our consumer's problem into the standard format in an optimization problem. This problem has two major pieces: the objective, which is what we are trying to maximize or minimize, and the constraint that limits our choices. The ST here stands for such that, so that it highlights the equation following it is a constraint to our choices. Now let's first focus on the objective part. In the objective, we will specify a few things. First, the max here, max, indicates that we're trying to maximize the function that's following it. Some applications call for maximizing something, while other applications call for minimizing something. So we will clearly state here that our objective is to maximize a function. Next, we specify the function that we're actually trying to maximize. In this case, it is the utility function of the consumer. And the utility function is determined by two variables, the quantities of each good, Q1 and Q2. So by changing these variables, the utility will change. And last but not least, notice how we outline two variables, Q1 and Q2, underneath the max sign. These variables are called the control variables. Just like the control knob you have on a TV or in a car, in this case, we're trying to maximize the consumer's utility by choosing quantities that they consume, Q1 and Q2. But we cannot choose the prices of the good or the budget the consumer has. In other words, P1, P2, and Y are the exogenous variables in this model. They're given to us. On the other hand, Q1 and Q2 will be determined by looking for the quantity pair that maximize the utility function under the budget constraint. So Q1 and Q2 are the endogenous variables to this model. In addition, once Q1 and Q2 are determined, we can also find out how much utility the consumer will get if they consume that particular bundle. And in that case, that particular utility value under those optimal choices is also endogenously determined by the model. So it is also endogenous variable of the model. In short, the optimization problem says that we're trying to choose Q1 and Q2 in order to maximize this objective function, while under the constraint that the quantities cannot be chosen such that the expenditure is not equal to our budget. Now our problem is formally specified. How do we solve it? Well, we'll follow a step-by-step procedure, which is called the Lagrangian approach. That is named after the mathematician Joseph Louis Lagrange. This method can lead us directly to the optimal solution of the problem whenever we can take derivatives of the utility function with respect to the control variables Q1 and Q2. A major reason why we're obsessed with derivatives in economic theory is that they greatly simplify the job to find optimal solutions. Loosely speaking, when the objective function behaves nicely, the derivatives will lead us to the optimal solution very easily. For instance, in the graph here, we have a single variable function f of x that is determined by its only argument of x. It is very smooth, such that it is differentiable with respect to x. And it is concave, because it is bending down. And if you connect any two arbitrary points along this curve, the segment always sits below the curve itself. It initially increases, and then peaks at this particular point of x star, and then decreases afterwards. The function has a very clear maximum. Let's call the special value of x that leads to the maximum of this function x star. Then we will notice that the derivative of this function with respect to x is positive for all these values of x that's leading up to x star, and the derivative is negative for all the x's that are past x star. However, when we evaluate the derivative at x star, the derivative is going to be 0. It turns out that this is not a coincidence at all. For any smooth function that reaches a maximum, it must be increasing up to that point, and then decreasing afterwards. And the derivative at the maximum must be 0. The same idea actually applies to minimums as well. As a smooth function dips into the minimum, it must be decreasing before that point, and then increasing afterwards. So the derivative of the minimum must be 0 as well. In other words, for a differentiable function, its derivative at the maximum or minimum must be 0. This is a very useful condition, and because it depends on the first order derivatives, this is called the first order condition, or FOC for short. So how do we use a first order condition like this to find the maximum of the function? Well, it turns out to be surprisingly simple, because the derivative of f of x with respect to x won't be 0 anywhere other than the maximum point or the minimum point. So we can just take a derivative of f of x with respect to x, which is usually a function of x as well, because you can see the derivative is constantly changing as the value of x changes. But on top of that, we already know that the function doesn't have a maximum or a minimum anywhere else. So if we force the derivative to be 0, there are only very few limited points that will satisfy that condition, and that will point us towards the minimum or the maximum. And on top of that, if this function is very nice, such that we know it doesn't reach minimum in the range of x that we're concerned with, then the resulting x must be pointing us to a maximum. And there we go. In other words, once you know the function behaves nicely, using the first order condition simplifies greatly the search for maximizing choice. And it simplifies it down to taking derivative of some objective function that you're trying to maximize or minimize, and then just solving this condition that the derivative is equal to 0. The conditions play an essential role in the procedure of the Lagrangian approach, and we'll see the repeated use of this first-order condition throughout the entire course in different models. Now we're ready to introduce the Lagrangian method. We'll first outline how it is used in a utility maximization problem without restricting us to any particular utility function. The benefit of not using any specific utility function is that it helps us highlight the step-by-step process that applies very generally. And after we gain a firm understanding of the process, we will then see specific applications to Cobb-Douglas utility function and other types of utility functions. So now let's delve in. Given a constraint maximization problem we've clearly specified here, the first step is to write down a function that combines the objective function and the constraint together. We'll call this function the Lagrangian, and we'll denote this function by the squiggly notation of L. The function is constructed by 3 different pieces. The first piece is just the objective function copy-pasted from the utility maximization problem. Without any specific functional form here to use, we will just write it is a general utility function that depends on Q1 and Q2. The second piece of the Lagrangian is an introduced variable, which is denoted by the Greek letter of lambda. This variable is called the Lagrangian multiplier because it is just being multiplied to our third piece here. Our third piece is essentially the constraint, but it is a modified expression of the constraint, where we simply subtracted the entire part of the expenditure from both sides of the constraint, and we cleared out the left-hand side. As a result, we'll just have y, which is our budget, subtracting the entire expenditure from the left. As a result, our constraint states that the expenditure should not exceed the budget. So this will be the modified version of the budget constraint that we'll put into the third place in the Lagrangian. And this is it. Now we have combined the objective function with the constraint into one equation, which is our Lagrangian here. And we'll use this to solve the optimal solution in the next step. Now with the Lagrangian written down, we're ready to write down our first order conditions. What we do in this step is just to take derivative of the Lagrangian with respect to all of our control variables, which are Q1 and Q2 in this case. But also we're going to take derivative of the Lagrangian with respect to the additional variable, which is the Lagrangian multiplier lambda. Now with 2 control variables and 1 lambda, we will end up taking 3 derivatives and yielding 3 first-order conditions. The idea is that, roughly speaking, we're searching along 3 different dimensions for the optimal solution, and the first-order condition needs to hold on each and every dimension. Now let's take a look at each one of these first-order conditions in turn. First, we're taking derivative of the Lagrangian with respect to Q1. Notice that Q1 affects the Lagrangian through 2 different channels. First, as we get more of good 1, the consumer's utility is going to increase, so that changes the utility function. However, on the other hand, the second channel that Q1 affects the Lagrangian is that every extra unit of good 1 consumer enjoys raises the consumer's expenditure by P1 units. So through this function, it's going to play through the constraint part of the Lagrangian. So now the derivative of the Lagrangian with respect to Q1 is going to be the derivative of the utility function with respect to Q1, which is the marginal utility of good 1. And also it's going to be the derivative of the Lagrangian multiplier multiplied by the constraint here with respect to Q1. And because it's linear in Q1, so the derivative ends up being minus P1 times lambda outside. And that's the second term we have. And that's our first order condition. The derivative of the Lagrangian with respect to Q2 is very similar. Q2 increases the utility of the consumer, but also increases the expenditure. So the derivative of the Lagrangian with respect to Q2 is going to be the marginal utility of Q2 through the utility function, and then minus P2 times lambda through the constraint portion of the Lagrangian. And there we have it. Now we can take derivative of the Lagrangian with respect to lambda. And notice that lambda does not affect the utility function at all. So the derivative with respect to lambda simply yields the entire modified constraint, and that's what we have here. And also notice that by forcing the constraint part to be 0, we're essentially getting our entire budget constraint back, which is equivalent to y is equal to the expenditure on both goods combined. Now, because we're searching for values of Q1 and Q2 and lambda that maximize the objective, we force each one of these derivatives to be 0. And that's exactly in spirit of our first order condition kind of idea. So, in fact, usually what we'll end up with is that we're going to have 3 equations and 3 unknowns. The unknowns being Q1, Q2, and lambda. This is not very obvious now because the utility function is abstract. But we'll see this very clearly in a few slides when we have a specific utility function. The key is that with 3 equations and 3 unknowns, we can solve for Q1 and Q2 that satisfies all 3 first order conditions. And with the intuition we established on the previous slide about first order conditions, if our utility function behaves nicely enough, which they are, then these values are the optimal choices we're looking for. Although we don't have a specific utility function here for us to solve the specific solutions for Q1 and Q2, however, it is still very useful to go a few steps into the solving process just to see the underlying mechanisms under this particular solution technique. First, we can rewrite the first 2 first order conditions, which we copy-pasted from the previous slide. The derivative of the Lagrangian with respect to Q1 and the derivative of the Lagrangian with respect to Q2 forced to be 0 here and here. So with these 2 first order conditions in place, what we can do is we can rewrite each one of them slightly by moving the lambda P1 and lambda P2 term with negative signs to the other side of the equality. Then what we end up with are the following. We're going to have U1 is equal to lambda P1 and U2 is equal to lambda P2. And now what we can do is we can try to combine these 2 equations into the same equation. One way to think about that is that when the second equation is satisfied, U2 and lambda P2 are essentially the same thing. They are taking exactly the same value. So let's call it a box for now. And now let's write down our first order condition here, which is U1 is equal to lambda P1. And because it is an equality, we can divide by exactly the same thing on the left-hand side and the right-hand side. It won't change the balance of the equation. But now the trick is, although we're dividing the same thing, they might be called different names. We're going to make use of the special value coming from the second equality when it is satisfied. So on the left-hand side of this equality, I'm going to divide the same value, but I'm going to call it U2. Or on the right-hand side, although I'm dividing by exactly the same value, I'm not going to call it U2. I'm going to call it lambda P2. And this is okay only because our second first order condition is holding true now. right? That's the piece of information we're getting from the second equation. So now once we have this relationship, what we will realize is that lambda and lambda will cancel out, and what we end up with is just u1 over u2 is equal to p1 over p2. And look at that. Absent of the negative signs, this is exactly our tangent condition from the graphical solution, that the marginal rate of substitution is equal to marginal rate of transformation. There is in fact an alternative way to combine these two first-order conditions. Because our first-order condition is u1 is equal to lambda p1, we can rewrite it as u1 divided by p1 is equal to lambda. And similarly, our second first-order condition is equivalent to u2 divided by p2 is equal to lambda. And what do you know? Combining these two things, because they're both equal to lambda, it must be the case that the per dollar marginal utility on good 1 is the same as the per dollar marginal utility on good 2. And that's exactly the same idea behind the tangent condition. Note how the tangent condition follows automatically from the Lagrangian approach. This is why I said that we don't really need to memorize the particular expressions of MRT or MRS, because the Lagrangian approach automatically takes care of that for us. However, it is still worthwhile to think through all those terms to gain a deep understanding intuitively about these objects so that we can understand and interpret the results coming out from these models. Notice that the third first-order condition simply gives back our budget constraint. And if we have a specific utility function, such as the Cobb-Douglas utility function that we'll see next, we can have very specific expressions of Q1 and Q2, and we can solve these inequalities to find a solution. And we should have our optimal consumption bundle. Now let's put the Lagrangian method to work with the Cobb-Douglas utility function. Let's say we have a representative consumer who has a preference relationship that can be represented by Cobb-Douglas utility function with a parameter of alpha. Moreover, the prices of the two goods are P1 and P2, and the consumer has a total budget of $Y. So what is the consumer's optimal consumption choice that maximizes her utility? To use the Lagrangian approach, we'll first need to write down our optimization problem very clearly. As you get familiar with the Lagrangian approach, writing down the problem clearly and correctly is in fact one of the hardest parts of solving the problem. Once the maximization program is correctly written down, everything else mostly follows very naturally. So in our maximization problem here, we have 4 pieces we need to clearly define. We need to specify, first of all, the max sign to indicate we're actually trying to maximize the utility of the consumer. We need to clearly specify what is the utility function we're trying to maximize. In this case, it is the Cobb-Douglas utility function that is specifically chosen here. The third piece are the control variables we're allowed to manipulate in order to maximize the utility. So the choices we can make are Q1 and Q2, and we need to clearly state that below our max sign. P1, P2, and Y are not listed here. That indicates that we're not allowed to choose P1, P2, or Y to maximize this utility function. The fourth piece, of course, is our constraint. That states the Q1 and Q2 has to be chosen such that it satisfies the budget constraint. And there we have it. Now, once we have these 4 pieces clearly specified, we have a well-defined constraint maximization problem. And now, let's write down the Lagrangian based on the information from this maximization problem. Can you try to write the Lagrangian yourself? Remember, it has 3 pieces. The first piece is objective function, which is our utility function. The second piece is the Greek letter lambda, which is our Lagrangian multiplier. And then the third piece is the part that is being multiplied to lambda, which is the cleared out version of the constraints. Can you try to write that down yourself? Please give it a shot. All right, let's compare notes again. This is the Lagrangian I wrote down. The Lagrangian in our case now is the objective function. Now it's very specific. It's a Cobb-Douglas utility function with the parameter of alpha, plus lambda, the Lagrangian multiplier, multiplied by the cleared out version of the budget constraint, which is budget minus the total expenditure on the goods. And that's it. Now with this Lagrangian written down, the next step is to take first order conditions with respect to the two control variables and the Lagrangian multiplier. So let's do that. Can you try to take derivatives of this Lagrangian with respect to those three variables? Please give it a try. Pause the video and write them down. Even if you got them wrong, it's totally okay. And in fact, it is very helpful. Let's try to take a few minutes to do this exercise. I'm serious. Did you do it? If you haven't, please do it. All right. Now, if you have written down your first order conditions, hopefully they will look the same as mine. I've double checked. These are right. The derivative of the Lagrangian with respect to Q1 is the marginal utility of good 1, which we have already calculated before many times, which is the derivative of the Cobb-Douglas utility function with respect to Q1. So the power alpha just comes down, and the power on Q1 becomes alpha minus 1. Q2 to the power of 1 minus alpha does not really change, and this is the expression for the marginal utility. The second component is Q1's impact through the constraint component, and that is minus lambda times P1. And we force this condition to be 0, and there we have our first order condition. The second first order condition follows very similarly, with the difference that we're taking derivative with respect to Q2. So the power on Q2, which is 1 minus alpha, comes down now, and the power on Q2 becomes minus alpha, because it's 1 minus alpha minus 1, which is minus alpha. And again, we've done this when we calculate marginal rate of substitution, so you should be familiar with this algebra by now. And of course, we have the component where Q2 affects the budget constraint component, and that's minus lambda times P2. Again, we force this derivative to be 0. That gives us the second first order condition. The third first order condition is straightforward, which is just the cleared out version of the budget constraint. Voila! Not too bad, is it? Now, with these three first order conditions in place, notice how each one of them is an equation of Q1, Q2, and lambda, Q1, Q2, and lambda, Q1, Q2, no lambda here. But we have three equations and three unknowns, and combined with a bunch of parameters that are given to us. Those are the alpha, the P1, the P2, and the Y. Now we can solve these three equations for the three unknowns, Q1, Q2, and lambda potentially. Now, just like what we did in a general approach, we're going to rewrite the first two first order conditions by moving the minus lambda P1 and minus lambda P2 parts to the right hand side of the first order conditions. By dividing the left hand side by the left hand side, the right hand side by the right hand side, the lambdas cancel out, and we end up with the tangent condition, where we have marginal rate of substitution equal to marginal rate of transformation. If you are confused about how we did the division of left hand side and left hand side, right hand side, go back and look at the previous part when we solve the general form of the utility function in Lagrangian, and you can check it out. Of course, you can also use the per dollar marginal utility equal to lambda kind of approach to get exactly the same answer. Now notice that this is an expression of Q1 and Q2 and a bunch of exogenous variables without lambda. And also notice that first order condition 3 here, or our budget constraint, is also just a function of Q1 and Q2 without lambda. This means we can use equation 3 and the tangent condition together. So we'll have two equations and two unknowns. So we can solve for both Q1 and Q2 by using 3 and the tangent condition together. To do that, I'm going to try to substitute one of these variables from the tangent condition into their spot in equation 3. And then we'll eliminate one more variable, and then we'll have one equation and one unknown, which we can easily solve. So to do that, let's just try to rewrite Q2 as an expression of Q1, and then we'll be able to substitute into equation 3. To do that, I'm just going to multiply both sides of the equation by Q1, and that will put Q1 on the right-hand side of the equation multiplied by P1 over P2, so that gives us this part. And then I'm going to multiply the reciprocal of alpha over 1 minus alpha on both sides of the equality, and that will give me Q2 is equal to 1 minus alpha over alpha times this expression. And there we have it. We're going to call this equation our equation 4. Now we can plug equation 4 into equation 3 to replace Q2. And when that happens, I'm simply plugging in this entire expression coming from equation 4 into the position of Q2 in equation 3. And that's here. Okay? And now they're combined into one equation with only one unknown, which is Q1. Everything else here are all exogenous variables: y, p1, p2, and alpha. Now we can solve this one equation for the only unknown in it, which is Q1. Now to find Q1, we realize that P2 and P2 will just cancel out, and we will have the same product of P1, Q1 here and P1, Q1 here. In other words, we can rewrite our combined equation here in the following way. We can write y minus P1, Q1 minus P2 times 1 minus alpha over alpha times P1 over P2 times Q1 is equal to 0. But we already said that P2 and P2 cancel out. And we have P1, Q1 here and P1, Q1 here. So what we can do is now rewrite it as y minus, there's a minus sign here and minus sign here. So we're going to have P1, Q1 being factored out of this. So we factored out minus P1, Q1 on the first term here, and that leaves us a value of 1 inside. We also factored out minus P1, Q1 here on the second term, which will give us a plus 1 minus alpha over alpha equal to 0. Now, notice that what we have inside here is just alpha over alpha plus 1 minus alpha over alpha. But what is that? Well, that's alpha on the bottom, and alpha plus 1 minus alpha. What's that? Well, that is just 1 over alpha. In other words, our equation is equivalent to y minus P1 Q1 times 1 over alpha is equal to 0. Well, but this is just equivalent to y is equal to P1 Q1 times 1 over alpha, which is equivalent to alpha y is equal to P1 Q1. Flipping both sides of the equation, exactly the same thing, just that we're going to put Q1 here on the left-hand side of the equation to seem a little bit more natural. Now we have this equation. P1 Q1 is equal to alpha times y. This equation has a very natural interpretation. It says that the expenditure on good 1, which is P1 times Q1 here, is in fact equal to a fixed fraction of the budget, which is alpha of y. Right? Of course, from this equation, we can solve for Q1 by just dividing both sides of the equation by P1. And that will give us Q1 is equal to alpha y divided by P1. Because now we have obtained an expression of Q1 that consists solely of exogenous variables, alpha y and P1, without Q2, without lambda. Therefore, this is actually a solution for Q1. It says that once you tell me what is alpha, what is y, and what is P1, I can tell you exactly how I should choose Q1 to maximize the utility. And this is it. So we're going to put a star on top of our choice Q1 here to indicate that this is an optimal solution to the problem. I'd like to note here that this particular feature, that the expenditure on good 1 is a fixed proportion of the budget, is a very particular feature coming from the Cobb-Douglas utility function. And this is not general. It actually drives a very special set of results, and we'll come back to this later on. I will also note that this particular fraction in the budget alpha is exactly the power on Q1 in the utility function. Now moving on, although we have solved for Q1, we have not yet solved for Q2. So with Q1 solved, what we can do is just plug our solution of Q1 star into either one of these equations that leads to the solution, either equation 3 or equation 4. If we plug in our solution back in this position or this position, we should be able to find Q2. So let's just plug it into the budget constraint, or equation 3 here. Can you please pause and give it a try? All right, if we plug in P1 star into the budget constraint, what we would have is y minus P1 Q1 minus P2 Q2 is equal to 0. But now we're going to plug in Q1 star into the position of Q1. So that will give us y minus P1 times alpha y over P1 minus P2 Q2 equal to 0. However, now P1 and P1 will cancel. Now what we will end up with is y minus alpha y minus P2 Q2 equal to 0. And this is equivalent to, after factoring y out, 1 minus alpha times y is equal to P2 Q2. And of course, now we have a very similar expression as before, and it just says that the expenditure on good 2 is again a fixed fraction of our budget y. And what is that fraction? Well, it's exactly 1 minus alpha, the power on Q2 in the utility function. And by dividing both sides of this equation by P2, we will find the solution of Q2, which is 1 minus alpha times y divided by P2. Again, this is an expression only consisting of exogenous variables, and therefore this is a solution for Q2. There we have it. To sum up the example, given the Cobb-Douglas utility function that has a power alpha on Q1 and power 1 minus alpha on Q2, the optimal choices for the consumer are given by these very precise expressions. The amount of goods consumers should consume to maximize utility are the following. The amount of Q1 should be alpha times y divided by P1, and the amount of good 2 should be 1 minus alpha times y divided by P2. And this is always an interior solution, meaning that the consumption on both good 1 and good 2 would be strictly positive because alpha times y is always strictly positive. and likewise for 1 minus alpha times y. Moreover, P1 and P2 are also strictly positive, so their ratios must be strictly positive. So in other words, if a consumer's preference relationships can be represented by a Cobb-Douglas utility function, then the optimal choice for the consumer will always be an interior solution. The consumer will never only consume one good without the other. If you stare at these expressions long enough, you'll realize that they are actually demand functions, because they tell us what the quantities the consumer would purchase to maximize their utility when they have a budget or income of Y and facing the prices of P1 and P2. Finally, as promised at the beginning of the section, we have formally derived demand functions based on a model of consumer behavior. Because these optimal choices are demand functions derived from the utility maximization problem, we call them derived demand.